Okay, so chapter 10 kind of switches topics a little bit. We're going to talk about the universe a little bit because we've been talking about fission and we've been talking about fusion, right? Where does fusion take place? Naturally. On the sun. So stars do this process. So this topic is not coming out of left field. It really is. We're going to talk about how fusion takes place and how we know the chemical composition and everything like that.
How many slides do you have?
21.
10 pages?
Okay, so first of all, let's talk about nuclear fusion. This is what we talked about last week, right? Nuclear fusion is the process in which two smaller nuclei combine to form a larger, more stable nuclei. Not always, but on our sun, we take hydrogen plus hydrogen, and what does it form? This is a review. So on our sun, we take hydrogen plus hydrogen, and what does it create?
H2?
Helium, right?
Oh.
Hydrogen and hydrogen fuse to form helium. Kind of? Are we starting to... That coming back to us from last week? That's what our sun does?
Sure.
Yep.
Okay. Basically, this is the process that powers most stars. Now, not all stars do hydrogen plus hydrogen giving us helium. That's why some stars are different colors. Not all stars burn the yellow color our sun does, right? So every star burns a little bit different colors based on what type of fusion they do. Okay, so in our galaxy, the Milky Way, this consists of between 200 to 250 million stars. Beyond our galaxy, there are approximately 1 billion other galaxies that also have stars. So, let's start talking about some astronomy. So as we look further and further and further out into space, we're actually looking further and further and further back into time. Because light travels, right? And it travels at a certain speed. Now, yes, it does travel at 186,000 miles per second. So, can we really see a difference in the speed of light here on Earth just from turning the lights on, so on and so forth? No, because it happens so fast. But when we're talking about the vast size of our universe, if things are billions and billions and billions of miles away from us, it could take some time for the light to finally reach us, right? So technically, the moon is 240,000 miles away. So the light that bounces off of it takes 1.3 seconds to get to Earth. Now that's a pretty small amount of time, right? That's not as big of a deal. However, the sun is 93 million miles away, so it takes it 8.3 minutes to reach Earth. Now that's a measurable amount of time, right? So if the sun were to quit working, it would take us 8.3 minutes to even realize that it was no longer producing light, correct? Because the light we would see is 8.3 minutes old. Does that make sense to everybody?
Are we just going to an ice age, pretty much?
Oh yeah, it would, like, everything would. Well, because, and we'll talk about it in just a second. You always like to get ahead of me. But basically, if the processes would stop on the sun, it would basically, gravity would kind of pull it all in, and so everything would kind of, I mean, that's kind of what happens in a black hole, is when the sun stops working. Now, so to put it in a little bit of a bigger...
Yeah. Oh, no. There's absolutely no chance.
Guys, come on. To put it in a little bit grander scale, Neptune is 2.8 billion miles away. So when we are looking at it, we are actually looking at what happened 4 hours ago. So when we see Neptune in the night sky, we're actually seeing what Neptune was doing 4 hours ago. And Neptune is in our solar system. So can you imagine how long ago it must have been for these galaxies that we're observing, how long ago that light was being given off? Okay. The nearest stars are 4.3 light years away. So what that means is we are seeing what they were doing 4.3 years ago. So if something changes, it's going to take a long time for us to see the effects here. Okay, so what is the universe made up of? Well, Aristotle thought that heavenly bodies could not be made out of the grungy elements that make up our Earth. They must be made up of something that is grander, and he called this ether. Today, we have evidence that the universe is made out of the same elements we have on Earth, and there are several different ways that we know this, and we're going to talk about each one. So first of all, the first piece of evidence is meteorites. Meteorites fall to Earth often from the asteroid belt between Jupiter and Mars, sometimes from other ones, but for the most part from that asteroid belt. When we analyze it and we study the elements that are made up from this meteorite, we have yet to discover an element that we don't already know of. Okay, moon rocks have also been analyzed. We've been to the moon, we've collected samples, we bring them back. We've also analyzed those for what their chemical makeup is, and again, we have found that they have the same elements that we have on Earth. Okay, we have been to Mars. We've sent rovers to Mars. The rovers on Mars have done experiments on the field, determine what the chemical makeup is, and again, they have not found any elements that we ourselves do not know of here on Earth. And then the last one is cosmic rays. We can study the light that other planets give off of, other suns get off of, how they reflect light. And we can see that they contain heavier elements than our sun does, but at the same time, they're all elements that we know of here on Earth. So as of yet, we have yet to find an element that we don't have here, which makes us think that all matter is made up of the same basic types of elements. All right, so we're going to spend a lot of time talking about light, talking about this last thing, the cosmic rays. So first of all, the biggest piece of evidence comes from looking at light. Okay, we can see light, correct? Do we have to do anything? Do we have to travel to the other planets to observe and test light? No, we can see it. Okay, we can study it right here. We don't have to go anywhere. Don't have to do anything. When white light passes through a prism, it is broken down into a rainbow. Starts at red, goes to violet. Everybody's seen a rainbow, right? Okay, well, if you shine white light through a prism, you should also see a rainbow. Well, what people started noticing is that when we put our sunlight through a prism, it would actually produce these things called a Fraunhofer line. Okay, and basically, that's these black lines in this rainbow. Does everybody see the rainbow from red to Roy G. Biv, right? From red to violet. Does everybody see the black lines? Okay, so it's like there are pieces of color missing, right? So what people noticed was in the 1800s, when we separated this, the scientists started to notice that there were these black lines that seemed to be an absence of color, and they actually gave these a name, and there were people out there who studied them, and they were able to identify 600 missing lines, which is kind of weird. When we see a rainbow, we don't see missing colors, right? We just see solid colors. So what are these missing lines? Well, we also noticed that when elements are exposed to a flame, they will give off a particular color of light. Every element gives off a different color when it is exposed to flame. So like, we're familiar with neon gases, right? Well, when we talk about neon gas lights, are we really talking about neon? No. Do they use neon sometimes? Yes, but they also use the other noble gases. Every noble gas burns a different color, so they produce different color lights. Okay, so they're using this concept. When you pass this light that the element produces through a prism, it produces specific bright lines, almost the opposite of that last picture I showed you, and I'm going to show you another picture in just a second. But the last picture had a lot of color with little black lines in it, right? Well, these guys, when you do this to an element, it produces a black strip with color pieces to it. So it's almost like the opposite. This is what scientists like to call the fingerprint of the element. Every element will give off a different set of lines, and every element, so when we're analyzing it, we can look at their set of lines and we can determine what element it is just by looking at the light it's producing. Okay? Well, what they then found was that these bright lines corresponded to the dark missing lines from the sunlight. So then we could ID the elements making up our sunlight. And we can use the same process for other sunlight that we can observe. So basically, here is what I'm talking about. Okay, we see at the bottom, we see these black strips of, down here at the bottom, right? We see these black strips. As we notice, we have color lines, right? You see all the color lines? Each one of these is representing a different element. So sodium produces a few blue lines, a few yellow lines, a few orange lines, and a red line. So every single time we see this, we can identify it as sodium. Hydrogen doesn't produce very many lines. It produces a couple of blue lines, a green line, and down here a red line. So every single time we see this, we can identify it as hydrogen because this is a fingerprint. Everybody has a different fingerprint. Every element produces a different set of colored lines. So basically, our sun is, for the most part, hydrogen and helium. Sometimes some byproducts, maybe a little bit of lithium occasionally when fusion goes a little out of order. But for the most part, it's not going to contain all of the other elements because that's basically what it is. It's hydrogen fusing and forming helium. So we shouldn't be seeing these lines on the spectrum. Okay, we should definitely see these lines, right? Because it's hydrogen. We probably won't see all of these lines because, again, like I said, the sunlight has black lines telling you that it's missing information. Well, the sun is only made out of 2 elements for the most part, so it should be missing quite a bit of information, correct? All right, another piece of information that how we can determine what things our universe is made up is radio waves. Okay, radio waves can be generated by cold gas between stars. So basically, when hydrogen is between stars, so think about how far apart stars are. Think about how cold it must be when you are that far from a sun, from a star. Okay, basically it slows down, and if it slows down enough, it should technically start to release radio wave emissions. Remember when we were talking about radiation 2 chapters ago? There were all these different wavelengths. Remember, radio waves were really long. They're not very harmful, right? So basically, when a gas slows down enough, it'll start to emit these radio waves because gases have a lot of energy, right? So that energy has to go somewhere. It doesn't just get lost. So if it's slowing down, that energy then gets emitted as radio waves that we can then pick up here on Earth. So from all of this, we were able to determine that the universe is 93% hydrogen, 6% helium, and less than 1% of all the other atoms. So the majority of our universe is hydrogen. So think about how much carbon we have in this room alone. And we're only in one room on one planet out of the entire universe. Okay, and that carbon, whatever's in this room, is less than 1%. So think about how much hydrogen there must be if that's only 1%. All right, so these lines that I was talking about, these are called spectra. Okay, these are fingerprints that tells us what stars are made out of. But it can also tell us some other piece of information. Just like we know what spectra hydrogen produces, we know what spectra sodium produces, so on and so forth. Well, they're not always in the exact same spot, but they're the same series of lines. So basically, they can get shifted one direction or the other. It's still the same line. So if we look at these lines down here, we see 2 in the blue, 1 up here, 3 in the yellowy green, 2 in the orange, 1 in the red. We look at the next one, we see 1 in the red, 2 in the orange, 3 in the green, 1 here, 2 in the blue, right? Do you guys see how it's the same pattern of lines? They're in the same color spot. It's just on this side, we see a difference in how much red is left over, right? On this side, we see a difference in how much blue is left over. Well, this tells us something. If the spectra shifts towards the red, so if we have less red, it's telling us that the planet or the star or whatever is moving away from us. Okay, if it shifts towards the blue, it's moving towards us. Okay, this is called the Doppler shift. Has everybody heard of Doppler before? A Doppler effect? Maybe. Wow, are we asleep? Yes, the radar Doppler. Okay, so we all know how this works, even if you don't know it yet. The Doppler shift, you guys hear it here on Earth by just listening. When a siren passes you, you pull over to the side of the road because you see an ambulance behind you, right? As it approaches you, don't you notice something as it passes you? What happens to the sound? It drops pretty quickly, doesn't it? It's like really loud, and then as it gets past you, the pitch of it completely changes, and it's not near as harmful to your ear, correct? As it's approaching you, the sound is scrunched. As it passes passes you, it starts to get a little bit more stretched out. And so remember, sound is like waves. Sound are waves. And so depending on how big the waves are is what sound you hear in your ears. This is exactly what I'm talking about when I'm talking about the light shifting. Okay, based on if it's moving towards you, or when it's moving away from you, will affect that wavelength that it gives off. Because remember, colors are wavelengths, right? Okay, well, these spectra shifts are studied. As galaxies are studied, red shifts are primarily noted, which means that everything is moving away from us. Okay, red shifts mean away, blue shift means moving closer. AKA, most of the stars seem to be moving away from us. There has only been a handful of galaxies that have been found moving towards us. And probably the only reason they're moving towards us is because they are gravitationally attracted to us because they're so close to us. Not being attracted to us for any other reason, just by gravity. So why does this happen? Well, they think that our universe is expanding. So, the way I like to explain it is, if you put a whole bunch of dots on a balloon and then blow it up a little bit bigger, don't all the dots separate from each other? You blow it up a little bit bigger, they just continue to separate farther and farther and farther away from each other, right? Okay, well that's exactly what they think the universe is doing. It's just gradually expanding, so everything is getting farther and farther and farther and farther away from each other. Okay, this leads us to why. There are several scientists just want to know why. Why is this happening? What caused it? Why are we expanding? We can see that we're expanding. We can see that things are moving away. Well, why? Okay, well, the first theory is called the Big Bang Theory, and this was actually a joke at first. The person who came up with it said, well, if that's true, then it must have just been like a giant explosion and it just went Big Bang and everything just started moving. So it was kind of like a joke at first. But then he started to realize that maybe that idea had some truth to it. So basically in this theory, it says that the universe had some beginning 10 to 20 million years ago. And it had some huge explosion that caused this expansion. So basically it's like all matter was in this really tight wound up ball. And something caused it to explode. And then it just went, all the matter started exploding out. And so technically, out there in space, is there anything that's going to stop the movement? No. So they're just going to keep expanding and keep expanding until eventually they start colliding with each other, or they're so far apart that we can't get to each other. Okay, there was another theory that said, this one is called the steady state theory, and this suggests that the universe had no beginning. It just was, and it's changing. It has always expanded, and it will always expand because new matter is created in voids between the expanding matter. Basically, this theory says that our density of our universe is staying consistent. So as things start to spread apart, where that void is, new matter is created. But it's not technically new matter because our density is staying the same. So it kind of accepts conservation of mass, not exactly. Okay, but this was before we had the technology to prove one or the other. So scientists would debate back and forth between the theories that they thought were true until 1865. Well, remember when we were talking about cosmic waves, microwave radiation? We were talking about how sometimes really cold gases will give off radio waves because they have slowed down their motion so much that they have to give off the energy in some way, shape, or form. Well, if this is true, then we should be able to pick up on them. That's what the scientists thought. So they thought that they would build a really big antenna and they would see if they could pick up on any of this radiation. Well, this actually happened by accident. Some scientists were attempting to build this microwave antenna to try to pick up some of these radio waves. But in the meantime, another group of scientists who already had a really big microwave antenna noticed that when they would turn it on, they had all of this interference. And so they kept trying to fix it. They kept trying to weld it a little bit better. They kept trying to make sure the machinery was plugged in correctly. They kept trying to fix it because no matter what they did, they kept picking up all this background radiation, kept picking up all these radio waves. Well, what ended up happening is they were picking up on these cosmic waves, these cosmic radio waves that the gases were producing. And there was no way to get rid of that because that's just what had happened. So basically, The scientists who were trying to prove this on purpose got scooped by people that were doing it on accident. The people who did it on accident got a Nobel Prize. But basically, this disproves the steady state theory. If it's a steady state theory and our density is staying consistent, then there would be nothing producing these radio waves. But we can see the radio waves, we can measure them, we can hear them, we can study them, so they're being produced. So basically, the steady state theory is no longer work, so therefore the scientific community started going towards the Big Bang Theory, and they decided that it happened about 13.8 billion years ago. Okay, so if we were just this ball of matter, what in the world would make us create all of the elements and protons and neutrons and electrons and all of the stuff that we have today? Well, there are several things that are also thought. First of all, something called nucleosynthesis. Basically, protons, electrons, and neutrons would have formed first. Okay? Then they would have started arranging themselves. The collisions would have taken place, creating heavier nuclei such as hydrogen, helium, lithium, so on and so forth, because those are the little elements. Those are the more basic elements, right? Those elements are relatively stable. Once we had a whole bunch of hydrogen and helium, we would start to form stars that would fuse the hydrogen together to create helium. However, not all stars fuse hydrogen together. Some stars fuse other elements together, so that therefore we could create other types of elements beyond just hydrogen and helium. Okay, when stars reach high temperatures, these are called red giants, they can then fuse helium together to form carbon. So if we had a star that produced temperatures high enough that we could take a helium plus a helium and we could produce carbon. Our star doesn't do that. The sun doesn't produce that as high temperatures, but there are stars out there that do. Okay, then after it would reach the end of its life, it would then contract, forming something called a white dwarf. Basically, it would run out of fuel. In our sun, we take hydrogen, we fuse it together to get helium, but there's only so much hydrogen. Eventually, we should use all the hydrogen up. So what happens when there's no more fuel? Well, the sun would then start to kind of condense in on itself because of all the gravity of all the elements, because of the mass. It would start to condense, and it would form a very, very hot small star. And then when all of the fuel was gone, it would just start cooling. Okay, it has no more fuel, just start the cooling process. Well, this cooling process would probably last for billions of years. So it probably took a while to create elements like uranium, so on and so forth, right? Okay, these red supergiants, these can produce higher temperatures. Okay, they're bigger, they have more mass, they have more fuel, they have more types of elements. Therefore, they should be able to fuse together different ratios of elements to form new elements. Well, basically, this can happen up until iron. Iron is so stable that basically once they create iron, they're in trouble. Because iron is not going to be able to go through this fusion process because it's already stable. Remember, the whole point in going through fission and fusion is to create more stable nuclei. Well, if iron is the most stable nucleus we have, then that's not going to work. So as the sun is producing iron, it's honestly killing itself because once it's into the iron form, it doesn't have any more fuel, and so eventually fusion is going to stop. Once it loses this battle, the gravity will start to kind of pull it all in again because it has so much matter, it has so much mass that it all just kind of starts reacting with each other, pulling it back in. Okay? And it will cause the star to kind of collapse. Now, based on how big the mass of the star is initially, we'll kind of decide what's going to happen next. Okay? This could create a rebound explosion. So as it going in and in and in, well, what happens as things start to condense? The interactions they have with each other increase. Okay? So as all these nuclei are hitting each other and compressing each other, eventually it could cause a rebound explosion, and this is called a supernova. So basically it's just like shooting all of the matter from inside the sun out into the surrounding area. This releases a lot of neutrons and energy, and this is how we create elements as big as uranium. Because remember, once the sun gets to iron, no other elements are created. But we know that there's elements that are created bigger than iron, right? Because we can see it on the periodic table. Well, these elements that are created bigger than iron are created in the supernova process, in this explosion where all this energy is released and all these neutrons are hitting these smaller type elements. Okay. Well, if this is a really big star, okay, if it's a really, really big star and we have this supernova explosion, after the supernova explosion, it depends on how big the star was to start off with. Our star is pretty small, so it would form a white dwarf, which would just gradually cool, and it would create gravity, and we would probably start migrating towards it, but it's not going to create something called a black hole. Okay, bigger stars that are a little bit bigger than us, they will form something called a neutron star. The atoms are squeezed so tight that the protons and electrons will be crushed together, and then they will basically form a whole bunch of neutrons. Okay, but again, eventually this process will stop because it doesn't have enough mass. But if we get to a really, really big star, these protons and neutrons are going to continue, protons and electrons are going to compress into neutrons, and then the neutrons are going to compress on each other until basically it's just kind of like implodes. And then it will have so much gravity that everything around it will kind of just start spiraling into it. And honestly, we don't know what happens when something goes into a black hole. We just know that it seems to disappear. But we know better than that, right? We know it doesn't disappear. We know it goes somewhere. We just don't know exactly where yet. So, yay, homework. You guys like my jokes that I've been starting to put on these things? Yeah. Okay, so page 179, numbers 1 through 10. There's not a whole lot of homework this chapter because, again, it was only 10 pages.